Good morning, students. This is our third lesson under the topic energy changes in physical and chemical processes. In our last lesson, we had looked at the bond breaking energies, then followed by doing some examples under the enthalpies of displacement, enthalpy of solution, enthalpy of combustion, and others. Today, in our lesson, under the same topic, we are going to look at the Hess law of constant heat summation. Hess law of constant heat summation will go directly to test the laws that we discuss some areas that expose us to how to apply the enthalpy of the Hess law of constant heat summation. That is, the law states that the enthalpy change for a reaction is the same whether it occurs in one step or several steps, as long as the initial reactants and products are the same. Students, in chemistry, we deal majorly in chemical reactions, and we have some products, industrial products, that we discuss that cannot easily be prepared directly in the laboratory, and their enthalpy changes for the formation cannot directly be determined. Therefore, a chemist by the name Hess came up with a law that tries to summarize and help us predict the heat change that can occur in a step. Let's look at the energy cycle diagram that we give, that's there on the board. That is the initial reactant. When initial reactant is converted to the final product, the enthalpy change to convert the reactant to give us the final product directly, delta H1, is equal to the enthalpy change when the initial reactant is converted first to an intermediate product, and then the intermediate product is further converted to the final product, that is delta H3. In summary, delta H1, in this case, enthalpy change for the direct formation of the product, is equal to that for the formation of intermediate and the next step that gives us the final product. Delta H1 equals to delta H2 plus delta H3. We can have an example to help us condense what we are trying to discuss. We have several reactions in which the formation of the final product involves an intermediate products. For example, when we are forming the carbon 4 oxide during the combustion of carbon. Earlier in Form 2, you had looked at the carbon and its compounds, and you discussed that carbon forms two oxides. When carbon undergoes combustion under limited supply of oxygen, normally we form carbon 2 oxide. When oxygen is in excess, the final product is normally carbon 4 oxide. Therefore, if the enthalpy of formation of carbon 2 cannot be determined directly by just adding oxygen and form carbon 2 to realize the enthalpy change, then we can make carbon 2 oxide become an intermediate product, then we oxidize carbon 2 to give us carbon 4 if we are already determining the enthalpy change for the combustion of carbon 2 oxide to form carbon 4. Let's look at an example. Calculate the enthalpy of formation of carbon 2 oxide using the following information. We are given when carbon is oxidized under limited supply of oxygen, it forms carbon 2. Carbon 2. And when carbon 2 is formed, carbon 2 can readily be oxidized by oxygen to form carbon 4. And the enthalpy change for the combustion of carbon 2 to give us carbon 4 is given as minus 283 kilojoules per mole. Carbon itself can directly be oxidized to give us carbon 4, and the enthalpy 1 be determined directly. To determine the enthalpy for formation of carbon 2, for the formation of carbon 2, first you need to present the information on an energy cycle diagram. On an energy cycle diagram, we have the initial reactant, that is carbon and oxygen, to give us intermediate product, that is carbon 2 oxide, and the final product in this case is carbon 4 oxide gas. What happens here? If carbon undergoes combustion under limited oxygen, then it forms carbon 2. If oxygen is adequately supplied in excess, then carbon can undergo oxidation to form carbon 4 oxide. In summary, what we had looked at earlier is that the enthalpy change delta H1 for the formation of carbon 4 is equal to that of the formation of carbon 2, then converting carbon 2 to carbon 4 oxide. Delta H2 plus delta H3 gives us delta H1, and that is mathematically presented as above. Therefore, if you bring the values for the enthalpies given in the question, where we have the enthalpy for formation of carbon 4 oxide to be minus or negative 393.5, that of combustion of carbon 2 to be negative 283.0 kilojoules per mole, then you can express it mathematically as 393.5 is equal to delta H2 minus 283.0, and this will help you obtain the required value here, that is delta H2, which is the enthalpy for formation of carbon 2 oxide. Mathematically, if you express 393.5 minus 283.0, you obtain minus 110.5 kilojoules per mole. The same information can be presented on an energy level diagram. As we had discussed earlier under energy changes, on drawing the energy level diagram, on the y-axis we have the energy that is measured in kilojoules per mole. Then on the x-axis we present normally the reaction path or the reaction cause. In this case, the reactions here, if you look at the enthalpy for formation of carbon 2, the value obtained was negative, showing that the reaction is exothermic. The enthalpy for direct combustion of carbon to form carbon 4 oxide also was a negative value, therefore it was also exothermic. The same applies for the combustion of carbon 2 to give us carbon 4 oxide. It tells us that when we are drawing the energy level diagram, the reactant will remain at the top, and then the products appear, the final product appear lower in the scale. And therefore carbon as to oxygen, the final product is extracted carbon 4 oxide. And therefore when carbon undergoes combustion under adequate supply of oxygen to form carbon 4, the enthalpy change is minus 393.5 kilojoules per mole. That's delta H1 presented as shown on the energy level diagram. For the intermediate product formation, that is carbon 2, the enthalpy change we obtained was a negative value. Therefore, the arrow showing the formation of the product appears just below the initial reactants to give us the intermediate product. And that applies to the oxidation of carbon 2 to form the final carbon 4 oxide. Since in each case here, in each step followed in the formation of the final product, the enthalpies were negative, then the arrows showing the formation of carbon 4 oxide from carbon 2 also faces down. And the enthalpy change, that delta H3, remains to be, or you indicate as minus 283.0 kilojoules per mole. Students, if you follow the steps clearly, then you should be able now to do our second example that will form the exercise for the next, that I will confirm in the next lesson. That is, calculate the enthalpy of combustion of methane given the following information. That is, carbon undergoes combustion to form 1 mole of carbon 4 oxide. The enthalpy of combustion of carbon there is given as minus 393.3 kilojoules per mole. When hydrogen undergoes combustion in air, it forms water, 1 mole of water. The enthalpy of combustion is given. Therefore, you are also the enthalpy change for the formation of methane. Students, you can try the example and we have to discuss it in the next lesson. Thank you for listening and you are welcome next time.